steps is the definition. Is understood as a set of rules, norms, requirements, materials, and processes that applicate a certain sequence allow to obtain and final products and integral circuits, which are the miniature electronic device. The first device is the field effect transistor. It's the most. It's a transistor used to amplify switch electronic signals. It's the most commonly used transistor in the microelectronic industry, entering an analogy of digital circuit. Although of the bipolar junctions, transistor was much more popular in the past. Virtually all commercial processors are based on MOSFET transistor. In this graphic, we can see the three pins most important in the MOSFET. We have source, gate, and drain. Internal compute are the metal, polysilicon, and oxide on silicon. In this graphic, we can see equations and functions. But this equation is different than the normal MOSFET because we can use the weight and lump above the MOSFET. For example, in drain currents, we can use we use the weight loss and voltage gain source and voltage off. How to explain design parameters? In this graphic, you can see the drain currents. It's different because we are used the lump and weight, because it's necessary to the values to obtain the current to work in the process. In these parameters, it's necessary to work in two zones, values, trial regions, and active regions. Each region is necessary to apply the equations. Let's add some colors. In this graphic, we can see how to see the MOSFET in external button. For example, we can see the channel P and N. We have one MOSFET, and another MOSFET is PPN. That is two MOSFET. When design a printed circuit, it's necessary to identify the components. For example, we can see the colors. In the first colors is the one MOSFET. Is the bronze P8 MOSFETs, and next MOSFET is P MOSFET transistor. We can identify the colors and come to compute the internal device. In this graphic, it is necessary the configuration of this. Basic fabrication steps in a nutshell. Some mass transfer imaging and design of the wafers. Do you something to imagine parts of the wafers, implements and impurities to change the electrical properties. Deposit metal insulator of the layers. Ground oxide plates and silicon oxide ambients. Edge putting supervise of topmost layers. And polish mega surface of wafer flats. The strip to imagine material business and process the next step. Layout design. Cheaper specific with a set of mass. Minimum dimension of mass determined transistor size is, for example, height, speed, cost, and power. Feature size is constant. It's very important because it's distance between source and drain. Set a minimum width on the polysilicon. feature size improves 15% every 3 years soon. The engineer rules segregations and 0.3 micrometers and 0.6 micrometers process. In this graphic, we can see the lambda 4 by 4 spacing width, and in 2 meters is lambda 4 with 4 and 2 meters. Remember that lambda is values in the 0.3 or 0.6. Design rules summary. First, metal diffusion have a minimum width and spacing of 4 by lambda. 2. Contacts are 2 dimensions. 2 lambda for 2 lambda and must surrendered by 1 lambda of the layers until below. Polysilicon use a width of 2 lambda. Polysilicon overlays diffusion by 2 lambda, whereas a transistor is designed and spacing for 1 lambda and width no transistor is designed. Polysilicon and contacts have a spacing of 3 lambda from another polysilicon or contact. And finally, and well surrounded PMOS transistor by 6 lambda and avoid NMOS and transistor by 6 lambda. Logic gates layout. Layout can be very time consuming. Design gates how to find together nicely with a library and standard cells. A standard cell design methodology, voltage, drain pipe, and ground should above the stand height. Advanced gates should simplify design rules, NMOS and button and PMOS and top. All gates include well and software contacts.
Invented standard cell layout. Usually the PMOS has with the 2 and 3 lines, the width or the DMOS, for example. You're looking 1 MOS and 2 MOS. A stick diagram. A stick diagram helps plan layout quickly. Need not be to scale. Drawn with color pencil and dry erase marker. And top Cooper and bottom Cooper. Within track. Where spacing. Within track and within track in the spacing required for wire for lambda for passing from neighbor equal 8 lambda. Bridge. Transistor holds consumer 1 writing track. In example, well spacing. Well must surround transistor by 6 lambda. 6 imply 20 between opposite transistor favor leave room for 1 white track. In the picture, looking the area estimate. Estimate area by continuing white tracks. Multiply by 8 in 8 lambda. For example, block 1 and block 2.
In this graphic, we can see the years when the first impressed circuits and in actual years. For example, in 1995, the first circuit weighs 300 nanometers. And actually, the weight is 77 nanometers. And in the future, we have weight 5 nanometers. In this one, we can see some examples. For example, the plastic elements, the resistor. This represents we have commons with weight and length. In what the circuits represent with this. The capacitor is necessary to use these equations. Capacitor value by capacitor per unit area. Another example is some components in a circuit. Okay? This is a resistor and CMOS in parallel. We represent op-amps and different input types. Finally, we can see designs. In this design is the 7 nanometers, and we have the voltage in a negative voltage, positive negative, positive voltage, and signal, and finally the out signal. Thank you. Okay, that's fine.